All right, so we are going to begin our final unit, Unit 6, which is the normal distribution. And today we're going to be looking specifically at uh, normally distributed variables. And so that's where we're going to get started here in lesson 6.1. So let's go ahead and begin. I want you to start by taking a look at this frequency table and the relative frequencies that go along with them. So if we take a look at a bunch of people's heights, maybe this is at a college, or it could be people at Homestead, although there are a total of 3,264 people, and we have their heights. Their heights go between 56 and 57 inches, 57 to 58 inches. Just so that you have a frame of reference, somebody who is 6 inches tall or 6 feet tall is 72 inches. Okay, so this might be looks like it's shorter than normal people, but we have 3,264 people, and this is how they break down. And then we have their relative frequencies, and again we get their relative frequencies by taking the frequency divided by the total. So I want to focus the highest frequency, the largest group here is the one at 559 between the heights of 64 and 65 inches, which is about 17.13% of the population. We're going to spend quite a bit of time, I think, looking specifically at this one here. There are 240 people in this group. Must be a college group that have a height somewhere between 67 and 68 inches, which is about 7.35% of the population. Notice that the sum of all of the relative frequencies is a total of 1. That's 100% of the population. And this is just how they get broken down. So then we can move to a relative frequency histogram, which has those same categories. Notice the highest range was between 64 and 65 inches. That was about 17% if we remember correctly. And the one that we were looking at was everybody between 67 and 68 inches, which was about 7.35% of the population. So this is a histogram, and then we can put this curve that kind of goes through the middle of most of those bars, just to kind of give us a shape of the data. And so you can see the shape here, the 67 to 68 is the area of this rectangle, which is kind of similar to the area underneath the curve that we superimposed on this frequency histogram. So we're going to talk more about the relationships between the curve and the histogram here in a little bit. Let's go ahead and talk about a normally distributed variable. It's normally distributed if it has a normal distribution. So in other words, if it has like a bell curve, it would be normally distributed. So not all variables are normally distributed. All of the distributions, though, can be described with what is called a density curve. And the density curve is the area or the curve that kind of summarizes all of the different bars in those graphs. So there's two properties about a density curve that we need to know about. One is that it's always above the horizontal axis. It's never going to dip below the horizontal axis. And second, the total area underneath the density curve is always 1. We can go back to here. We know that all the probabilities, all the relative frequencies add up to 1, and all of the relative frequencies are these bars. So all the areas of these bars add up to 1, and if the superimposed normal curve is a reflection of those bars, then that has an area of 1. So what that means is that even if it's not normal, the area underneath a curve, a density curve, is always equal to 1. So that's what we're talking about here, these density curves. And it's always equal to 1. It'll always be above the x-axis. So then we have different parts of a density curve. So we can have parts of a density curve that represent things that are above or below a certain x value. So for example, we have three different examples here. The first one, part A here, is the percentage of observations that are less than a number. So if C is a particular number here, all of the population that's below that would be the area, the percentage of the population below that would be the area that's underneath that curve. And if we have another one here at a certain age of D or a certain height of D, all of the percentage of the population that is taller than that would be the area of that curve. And we can even go between two numbers. Between the heights of two numbers, the area of the curve is going to represent the percentage of all of the people that are between those two heights. And so the normally distributed variables on a normal curve, and this slide just basically says what I said. The percentage of all possible observations that lie within any specified range is equal to the corresponding area underneath the normal curve. And so this is true whether it's normal or not. And so this goes back to that relative frequency histogram. Everybody between the ages or between the heights of 67 and 68 are going to be somewhere within the normal curve. That is the area of this normal curve, which is this area in here. I could open that up and say, well, what percentage of the population is going to be between the heights of 61 and 64? Well, here's 61 and here's 64. And so the percentage of the population that has heights between those two heights is going to be this area here, that is that new red area. So anyway, if we move forward, hopefully this is a review for you guys. Standardizing all normal curves. We talked about z-scores before, and a z-score always has a mean of 0 and a standard deviation of 1. So you can be 1 standard deviation or 2 or 3 standard deviations above the mean, or you can be 1, 2, or 3 standard deviations below the mean. And so we also want to review how do you take a random x value and convert it into a z-score. And this is something that we had, I believe it was in Unit 3 or Unit 4. But the z-score is always equal to a standard variable x, so just a random number. It could be a height, and then we would subtract the average. So this is the average, and we're going to divide it by the standard deviation. And so here are some examples of what that might look like. So all of these are normal distributions. Okay, they have different means. So for example, here the green one has a mean of -2, and it has a standard deviation of 1. And so for example, I don't know what this would represent, but if I wanted to find a z-score for any number, I would take x minus -2 minus a -2, which is x plus 2, and divide that by the standard deviation, which is 1. Okay, here's another normal distribution, and it has a mean of 3. So the middle number is 3, but its standard deviation is 1/2. And that makes sense because it's more scrunched together. And so it's not spread out as much. And so to find any z-score with that particular data set would be x minus 3. That's the average divided by 1/2, which is the standard deviation. And then finally, another normal distribution here. Now this is a normal distribution still. The shape looks kind of the same because it's a bell-shaped curve, but it's more spread out, and the average is higher. So the average is at 9, and the standard deviation is 2. So all of these are normal distributions, and all of them can be standardized to this right here. All of them we could standardize it and say that the z-score for all of them is 1, and they all have a mean of 0. It's just all those would represent different things. And so that's what we're meaning when we talk about a normal distribution. It can have different means and it can have different standard deviations, but to normalize it is a way that we're going to use to find the area underneath those curves to find percentages of people between certain heights or between certain IQs, or the percentage of people that are over a certain weight. And this is used a lot, but we have to normalize it first. And so that's what 6.1 is about. Let's just take a look at this again. Here we have two normal distributions, and we have the distance from A to B. So we have the actual data would be this graph here. We want to normalize it. So to normalize it, the average here becomes 0, and all of the scores, all the x values we can find the z-scores by using these formulas here. The specific number minus the average divided by the standard deviation, and that would give us a normal curve which looks like this. And we already know some of the areas on a normal curve, like for example between 1 standard deviation above and 1 standard deviation below, we know that that's about 68% of the population. And then 95% of the population is within 2 standard deviations of the mean, and 99.7% of the population would be within 3 standard deviations of the mean. That is 6.1, and the homework assignment is in Math Excel, and hopefully you do well on that, and we can go over questions about that next time.